Okay, so today we have Anindya to tell us about sparsifying Gaussian processes.
Yeah. Thank you for having me here. So I'm going to talk about sparsification of Gaussian processes, which is joint work with Shivam Nadimpalli, who is in the audience, and by O'Donnell and Rocco Servedio. I think Rocco is on Zoom, at least somebody pretending to be Rocco. Okay, so let's start. So let's start with the basics. What's a Gaussian process? It's just a collection of random variables. We are indexing our random variables with the set T if any finite linear combination of these random variables is a Gaussian. Okay, so examples, of course, include if you take any finite collection of jointly normal random variables, that's the Gaussian process, the standard Brownian motion, those are all examples of Gaussian process. Okay, and we will call a Gaussian process centered if for each of these random variables, xt has expectation 0. So so in this talk, we will think about the specific kind of Gaussian processes, which are called canonical Gaussian processes. So this is what's a canonical Gaussian process? So think of a set of vectors in the L2 space. Again, we are indexing the set of vectors by the set T. It could be a finite set, it could be an infinite set. And the corresponding, we can now define a Gaussian process xt, where the xt is given by the inner product of G with Vt. What is G? G is the standard Gaussian in that space. So each coordinate of G is an independent standard normal. Okay? So this is a very canonical way of generating a Gaussian process. Okay, because if you define your random variables like this, then any linear combination of these random variables, any finite linear combination would be a Gaussian.
The same G for all of them.
Yeah, the same G for all of them. So you have an n-dimensional, let's just think of an n-dimensional space. You generate a standard normal in that n-dimensional space, and then you take inner product with each. To get the tth random variable, you take inner product of this Gaussian with the tth vector.
That's the only way to give this a general.
So if the set T is countable, then any Gaussian process can be seen like this. Okay, it's not true T is not countable, but this talk we're just going to think of T as countable. In fact, I'm not getting into technicalities. I just think of the case when T is finite. Okay, we don't lose any generality, but potentially many of these things could be done when like T is even uncountable. So now, once we are thinking about these canonical Gaussian processes, there's a very natural, the vectors and the Gaussians are in one-to-one correspondence, in the sense that if you look at the variance of any Gaussian, the tth Gaussian, the variance of the tth random variable it's the same as the squared norm of the vector Vt. And similarly, if you look at the covariance of, let's say, xs with x sub t, is the inner product of the two vectors Vs and Vt. And since the Gaussian process is completely defined by its variance and covariance, so these vectors, the geometry of these vectors completely determines the Gaussian process. Okay? So first of it. And again, we are thinking of centered Gaussian processes, so everything has to mean 0. Okay? So that's why the variance and covariance completely determines what's going on.
But it's basically a symmetric matrix.
Yeah, it's a symmetric matrix. Defining the covariance matrix, you can either write down the covariance matrix or you can give the singular value decomposition of the covariance matrix. Really. So in particular, when studying Gaussian processes, a thing that has been studied extensively is the soup of a Gaussian. So you look at this random variable, which is the supremum of all xt as t goes across t. Okay. And this particular random variable has been extensively studied, starting with the work of Dudley, Fernie, Talagrand, and has applications in many areas, including random matrix theory, metric embeddings, computer science, many areas. It's a fundamental object that has been studied. So I'm not going to go into all the ways this study of this random variable has been effective, but let me just give a couple of more definitions. So one is that given a Gaussian process, again, x sub t, we will define its Gaussian width to be the expectation of the supremum. Just the terminology, we call the Gaussian width as the expectation of the supremum. And if you look at many of these works, which I haven't cited, but it just place a vague reference to, they basically tell us that if the set T is simple, it's somehow, we'll see what we mean by set T being simple, but if the set T is somehow simple, then the Gaussian width is small, okay? I'll give you examples of this. And in this talk, what we're going to do is we're going to explore like the converse theme a little bit. Namely, suppose I told you that the Gaussian width of a Gaussian process is small. Does it somehow mean that the set T is simple? Okay. And indeed, like, there are many works along both these things. So let me now get concrete with what I mean.
So, but Anindya, it's important that you did not normalize your vector.
We will normalize, we did not normalize our vectors. We don't need to normalize our vectors, but you can normalize if your vectors if you want to.
It won't change the problem.
It won't change the problem much. So we will normalize, we'll normalize, but it's not going to be a major issue. So let's just get a sense of like, how the Gaussian width varies with different sets of vectors. Let's take two extreme examples. The first example is, suppose my set of vectors Vt are just orthonormal unit vectors. Well, then the expected soup, you can just easily calculate this, is order of square root of log t. Okay, and indeed for a set of t vectors, this is the maximum value that the expected soup can have. Informally, like, if you're trying to maximize the expectation of the maximum, you should have like all your Gaussians in independent directions. Okay, and this is formally true. The other extreme would be that suppose all my vectors are actually unit vectors. I'm not even putting a bound on how many vectors there are. You can have all of infinitely many vectors, but suppose they all lie in a d-dimensional subspace. In fact, just think of the case when your vectors are the set of all unit vectors in a d-dimensional subspace, or d is small, let's say 3 or 4. Then the expected soup is actually just square root of d. It doesn't matter how many vectors you have, you can just easily check. Is the expected soup would just be square root of d. So this is saying somehow like, if the system is low dimensional, the expected soup is going to be small. If the system is high dimensional, the expected soup is going to be large. These are two extreme examples. But the correspondence between dimension of the underlying set of vectors and the expected soup is not extremely obvious, in the sense, maybe if you take a time, like an interpolating example, where the set of vectors are approximately low dimensional. So let's say I have again t vectors. Now, all of them basically have a huge component along E1, and they have a square root delta fluctuation along an orthogonal direction. So they're approximately like all one-dimensional. Then what would happen? The expected soup is constant, of the order of constant plus square root of delta log t. So what this says is that if t becomes really large, like, bigger than basically 2 to the 1 over delta square, or 2 to the 1 over delta, then this expected soup will start getting dominated by the fluctuations. But as long as t is relatively small, it will get dominated by this big term we have. Okay, so this gives like 3 examples really of how dimension or the approximate dimensionality could affect the expected soup. And now with that, let me state our main theorem. So the main theorem is that suppose you start with any set of vectors in R to the n. I'm not putting a bound on their cardinality. And this is consider the corresponding centered Gaussian process. Okay? Choose a target error epsilon. Then there's a subset of these vectors and suitable real numbers, CS, where we only choose exponential and 1 over epsilon. So we're choosing a set of vectors whose cardinality is independent of the dimension we started with, such that the soup of the original Gaussian process is well approximated by this non-centered Gaussian process, which is low dimensional. The error metric we are using is that the expectation of the absolute values of the gap is at most epsilon times the Gaussian width of the original process used. Okay. You can, instead of upper bounding the expectation of the absolute value, you can use L2 square error, any other error, high probability error. This will all be basically the same thing. It's really most of the, any other error metric would basically will have the same guarantee. So I'm just using the simplest to state thing that the expected absolute value of the error between the original Gaussian process, the target Gaussian process, and this approximation is small in terms of the Gaussian width. The key point is that the number of vectors we are using here is independent of the target dimension. Does this make sense?
And the shifts are essential.
Shifts are essential. So let me say that the shifts are essential. If you insisted on not having shifts, then the examples we saw earlier would tell you that you cannot, like, get any finite approximation, any good reasonable approximation while using only a constant number of vectors. I'll get, however, there's a way to avoid the shifts, but do something else. I'll get to that. Is the content of the theorem clear? The main thing is that the quality of the number of vectors we are using is independent of the dimension. You can write it in a slightly different form. So this is a particular form I think is interesting, that you can, from the expected expected absolute value of the error being small, you can also show that with high probability, the original Gaussian process, the soup of the original Gaussian process versus its approximation is within 1 plus minus epsilon factor, with probability at least 1 minus epsilon. So this basically says that the Gaussian width is kind of, you can normalize things so that the Gaussian width becomes 1, or the vectors have at most 1 magnitude. This is just saying normalize, you're normalizing things to get this kind of. It just follows as a direct corollary of what I stated earlier.
Also, the direction of the soup will be the same, or approximately the same. Not just the magnitude.
I'm not looking at the magnitude. I'm looking at like the
actual vector.
I'm looking at the actual value. I'm not looking at plus 1. I'm not absolute values.
So value, not the vector. I think Abhi is asking, is the direction in which G is maximized also preserved?
Yeah.
Direction in.
So you have Gaussian and you are taking the expected maximum of G dot V over V.
Okay.
Is the maximizer vector itself also preserved?
I don't think, I do not know if we have that kind of fine control. I would say no, really. And probably like it's approximate. No, I mean, almost certainly no, because what if, like, you have n vectors to start with? I mean, 1 over n fraction of the times. This would be like, yeah, you could never approximate the vector maximizer with constant number of vectors. But
also, since I paused you already, is this, like, given your previous slide, is it like x 1 over epsilon is required? And
so x 1 over epsilon is required. We do not know if doubly exponential dependence is required. And I do not know which way we believe the right answer is. Okay, but exponential 1 over epsilon is required. Doubly exponential might be necessary. So far, still non-centered approximations. There's a way to get centered approximations. That is, you can, since we started with an original Gaussian process, a centered Gaussian process, you can make sure the approximator is also centered, but then you can no longer go with a subset of the vectors you started out with. You will have to create a new set of vectors. So basically what you would do is you will take those constants and create fake vectors which are almost that constant. So if you instead of doing like a proper approximation, if you allowed improper approximation, you can create centered Gaussian process and have the exact same guarantee.
You have an example of an application of this Sparsification?
So I'll give one. I'll give a couple of examples. I'll give one example. A couple of examples. So one thing is, like, so this will lead to that example. If we start with a symmetric set of vectors, so by symmetric set of vectors, I just mean if Vt is in the set, minus Vt is also in the set. So that way, the soup of these Gaussian process is always a positive, non-negative number, because you're always putting Vt and minus Vt. So then our construction will also, the approximator will also be a symmetric set of vectors and have the same guarantee. And what does this entail? This entails the following, that any norm over R to the n can be, phi x can be written as an inner soup over a symmetric set of vectors T, inner product of V with x. Any norm over x can be written like this. So what does this imply? This implies that if you start with any norm over R to the n, there is for any target error, there's a corresponding low dimensional norm. The low dimensional norm being this norm just looks at some exponentially 1 over epsilon dimensions such that this low dimensional norm approximates the original norm with multiplicative factor 1 plus minus epsilon at 1 minus epsilon fraction of the places.
So in a norm, this metric set is usually a body, convex body, it's not a finite set.
It would be, we do not really require T to be a finite set. The entire thing will work like, as long as you have a set of vectors T. So we don't really require it to be a finite set, but there is a set of vectors T where the norm will be defining this.
Yeah, but usually norms are defined by, you said maybe countable. Normally norms are defined by some convex. But
Any symmetric convex set can be used to define a norm, right?
Any symmetric convex set can be used to define a norm. You can, in the limit, you can always you can get it to arbitrary accuracy using a countable set. Yeah. And again, I don't think it's really all we require is a canonical Gaussian process. I just don't want to make incorrect statements. So I'm trying not to say, but I think most of this should go ahead with go forward, even if for any canonical Gaussian process, this is fine. So even if the underlying set T is uncountable. So this is basically saying that any norm, if you look at a Gaussian space, is basically a constant dimensional thing. It can be well approximated by a constant dimensional norm. Okay, so for example, the L2 norm is, of course, like on the Gaussian space, it's essentially a constant, really. But a constant dimensional norm can approximate it.
So I'm confused about this statement. I feel like I might be doing something silly. But the sparsification clearly depends on psi, right?
The sparsification will depend on the target norm phi, yes.
Phi, yes, correct.
Yes.
So then why isn't this why can't I just output a single number?
No, you have to output a function which pointwise approximates the norm everywhere.
Oh, I see. I'm working with high probability, not just an expectation.
You don't want to get the expectation of the norm correct. You want to get the norm correct everywhere or almost everywhere.
So what will it look like for L infinity?
L infinity, well, L infinity norm will actually just be, it's actually highly concentrated so it will just be a constant number. Because over the Gaussian space, the standard Gaussian space, it's just root log n. I think this is root log n, right? If the L infinity norm with high probability is just basically root log n.
So you could output a single number.
You could just output a single number.
But you could kind of my confusion.
Yeah. But if you think of a norm like absolute value of x1 plus absolute value of x2 square. Well, that's a low dimensional thing, so it's still covered by this thing. Well, that was actually the only application I listed, but I can give you one application which I haven't listed, which is actually was the starting point of this project. That if you take any polytope over R to the n, which has constant geometric width, so means all the separating hyperplanes are at constant distance away from the center, then it can be using this term plus a little more, you can show that it can be approximated by a constant dimensional polytope. So a constant width polytope can be approximated by a constant dimensional polytope. If you're familiar with this kind of CNF, DNF kind of things, this is very analogous to the statement that a constant width CNF can be approximated by a constant size CNF.
No, but that's after randomization. In the CNF, DNF world.
It's
not that you can use it, it's not true without any restriction of the variable.
Without any restriction.
CNF, yeah.
Maybe I'm then misstating the thing. Shivam, what did I want to say, or am I mistaken?
Statements are analogous. In the CNF, TNF proof, there are restrictions.
Yeah, so in the polytopes there are none. So it's not so analogous.
Okay.
I don't think you need restrictions. No, there's just this is like a Gopal and Mecca Reingold sparsification kind of stuff, or Levet Wu Zhang sparsification. You don't need restrictions.
I don't want to take sides here.
Okay, so, yeah, I don't know what you are the equivalent in terms of width. We can discuss it after.
Okay. So sorry, one more. Is the following interesting / correct? So one corollary of your theorem is that, with high probability, any norm basically takes only x of x1 over x1 over epsilon different values with high probability.
Well, maybe three exponentials would be required, because if it's like, if it's a L dimensional thing, you would expect it to take maybe, I don't know, 2 to the L different values. I'm just saying it was like it's only
okay.
So maybe any norm essentially with a small error would take like, these many different values.
Still
constant. Not even a tower, still like yeah, I do not, that's true. I do not know how, if this was like easier to prove by some other method, but
yeah, I mean, you usually find things concentrating. That's why like this false intuition that there is only one value. But I guess in some sense you're saying that, okay, not one, but constant value.
Yeah, constant number values, things will constant values. Okay, so those are in terms of applications. I just wanted to say, in terms of upper bounds, all our approximators have this doubly exponential dependence on epsilon. And it doesn't matter what you do, even if you start with a set of unit vectors and you allow yourself to choose a set of different vectors and allow offsets, still getting an epsilon error with expected epsilon times Gaussian width error would require at least exponential in one of epsilon different vectors. So the upper and lower bounds are currently off by an exponential factor, and I don't think we have a very clear intuition as to whether the upper bound should be tightened, can be tightened, or the lower bound can be tightened. But at least you cannot get poly 1 over epsilon, different things. Maybe I mean, this is maybe slightly okay, yeah, no. Right, this is already, again, if you go by that analogy with CNF, DNF sparsification, this is already different from what can be done in that world where you can get, I think, logarithmic in 1 over epsilon dependence if for the error for the approximator. Whereas here you require exponential. But anyway, that analogy is like it's fine. So far, so good. So the rest of the talk, what I'm going to do is I'm going to prove the main theorem. All the other things I said are pretty much like, not very different corollaries of this main theorem. So let's just recall what the main theorem is. I have given you a set of vectors in R to the n. I look at the corresponding centered Gaussian process, which is just taking a product of G with Vt. I'm claiming that there's a subset of size exponential 1 over epsilon. So some constant, I'm not going to think too much about it, some constant dependent just on epsilon, such that the original Gaussian process is well approximated by this small set, the small Gaussian process. That's the main. And the error is going to be epsilon times the expected error is epsilon times the Gaussian. So first thing I'm going to do is that I'm just going to rescale all my vectors so that the Gaussian width becomes 1. So I'll just choose whatever be the Gaussian width, I'm going to choose that as my rescaling constant, so that now when I look at this new Gaussian process, the Gaussian width becomes 1. So now I have a Gaussian process, potentially infinitely many vectors whose expected soup is 1. My goal is to find a small set of vectors, small subset of those, and suitable constants such that the original process can be approximated by this new sparsified process, the error of so on. And my goal is just to keep the size of the set of vectors I choose independent of the target dimension, or independent of the ambient dimension, or independent of the set of size vectors exception. But basically, we're okay right now with any dependence on epsilon. So how do we go about doing this? So let's think about the obvious thing. We have a set of vectors T in the space, then potentially high dimensional space. I'm looking for a low size proxy for it. So the natural thing is to try to cluster the vectors in some way. I have many vectors. I want to cluster the vectors with a small subset, and hoping that maybe if I cluster the vectors with constant number of clusters, maybe I can just pick 1 vector per cluster, something like that. It's natural to try to cluster the vectors like that. So let's again do the obvious notion of clustering. Namely, I have been given a set of vectors. I'll try to create a delta covering for the set of vectors. Okay. By delta covering, I just mean I just want to make divide my vectors into balls so that the diameter of every ball is no more than 2 delta. So this is my set of points in the space. And let me do the clustering, the obvious clustering. And let me have these balls. All of the balls, suppose we assume that they have diameters at most 2 delta. The radius is delta. So suppose now what we have is that, suppose this delta covering, I don't know how many clusters it will create. Let it create m clusters. Okay. I'll call these clusters as B1 up to Bn. For each of these clusters, let's say the SF cluster B sub S, I will choose one of the vectors from there, B RS. So I'm calling it RS as the representative of the SF set, calling it B sub RS. This is so maybe like, this is my clusters in the space, and for each of the clusters, I choose one of the orange dot. So one vector per cluster. Of course, I don't know how many clusters I've created. Maybe I've created too many. But now what is the purpose of choosing these representative vectors? Well, for each cluster, I choose a representative vector VRS. And now observe that the soup of the Gaussian process restricted to vectors within this cluster is the single Gaussian corresponding to the representative vector plus the soup of V ranging over Bs, G inner product is V minus VRS. I'm just like doing the subtraction, nothing more. Right? But now the nice thing is that each of the vectors appearing in the second term has norm at most 2 delta. That is because I have a delta coupling, right? So if I have a delta covering, then when I choose a representative vector within that set, V minus VRS has norm at most 2 delta. What does this do? Well, so now I'll write down this one. This is the reason it's important, useful is because of this property of Gaussians, that whenever I have a set of vectors whose norm, let's say, is bounded by kappa, then the Gaussian process is highly concentrated around its mean, where the concentration is independent of how many vectors I start out with. So for example, so what this is saying is that the soup of the Gaussian process, G inner product with WT, deviates from its expectation by more than T, with probability at most 2 e to the minus tau square over 2 kappa square. Well, this is like the concentration. In particular,
These two T's are unrelated.
Sorry?
There are two different.
Right. Okay. These two T's are unrelated. Sorry. Those I shouldn't have used the same T. Okay, I can't edit this now, but those two T's are unrelated. The T in the deviation is unrelated from the exact same thing. In particular, what is it saying? It's saying that if you look at the Gaussian process corresponding to G inner product with WT, its variance is small. It's at most, it's just the square up to constant factor, just the square of the largest vector. It doesn't matter how many vectors I have. Okay. So this is very important. And this is just follows from the Gaussian concentration inequality for Lipschitz functions. Okay.
This is something classical.
Yeah, this is well known. This is well known. It's Gaussian, any Lipschitz function over the Gaussian space is concentrated where the deviation is just dependent on the Lipschitz constant. And if you look at soup of or maybe can I write here?
Yeah.
Okay. So if I look at soup of inner product of W1 with X, WT with X. This as a function, if I call it just f of x, the Lipschitz constant of this function, the Lipschitz constant of f is at most the max of the norm of the wi's. This is easy to see. So what I'm saying is the Lipschitz constant is just dependent on the largest vector that appears there, and consequently the variance is just bounded by the two norm of the largest vector. Yes, it doesn't matter how many we don't have to pay union bounded.
You don't need this factor of 4.
I don't, I think the factor 4 might be, I do not know if the factor 4 is essential or not. But it's not going to be very important for us, the factor 4. Okay. So coming back to why this is useful, so note we were saying within each cluster, I have a Gaussian process sup G inner product with V, and you're saying, okay, we choose one of those vectors just arbitrarily and write it down as G of inner product with G inner product with that representative vector plus the sup over the difference Gaussian process with the difference vectors. But because those difference vectors are at most 2 delta in magnitude, what I can do is I can just replace the second term by its expectation, and I will have very small error. So if the expectation, whatever be the expectation of this thing, whatever be the expectation of sup of V, be it is G, B minus VRS, whatever be the expectation, I'm calling it C sub S, that the Gaussian process is within that cluster is well approximated by G inner product with VRS plus CS. The total error is going to be 4 delta with in expectation. Does this make sense? I'm just saying I'm going to replace the second thing by constant. This is the source of that constant. So moral of the story so far is that we have created a covering of our set of vectors. For each of the clusters, we have chosen a representative vector V as a cluster VRS. And then there exists some suitable choice such that within each cluster, the sup of the Gaussian process is approximated by a single Gaussian plus a constant to error 4 delta. Okay. Within each cluster, it's well approximated by a single Gaussian plus.
And you still didn't use the width bound.
I still haven't used the width bound, it will come later. So in each cluster, I have a suitable approximation by a Gaussian, non-centered Gaussian. So now what's the obvious thing we should do? Well, since each cluster sup is approximated by a single Gaussian plus a constant, I can approximate the total sup by a sup of these representatives. The number of vectors in this approximation is m, whatever be the number of clusters I've created, about which I have not put any bound so far. And what about the error of this approximation? Both the things are there. I have not put any bound on the total number of clusters, and I don't know what the error of this approximation would be. Within each cluster, the error is delta. Within each cluster, the error is delta. And now we're going to say, okay, the total error of our approximation, if I have m clusters, within each cluster, the error is delta. The total error would be delta times square root log m. It's not delta times m, it's delta times square root log n. The reason being that if intuitively the idea is that within each cluster, the error is delta, the worst way for the error to grow is to have all these errors in independent directions. That's the worst way for the error to really grow. Okay? This can be formalized using Slepier's inequality, but the error is essentially maximized if the error is from each cluster is not. So if you have created m clusters, if you have created m clusters, the total error would be delta times square root log n, and the number and my approximating set would be of size m. Okay. So really it depends on what m is. If m is small, like 1, 2, 100, we are good because the number of clusters would be small. So I have a sparse set for the approximator, and my error would be delta times square root log n. So what is the value of m? So far so good.
If I even ignore the exact constant that you need, you really want to just say that m depends on epsilon, like not
M only depends on 1 over epsilon.
yeah.
M only depends on my final target error, and I can tolerate. The point is that I can, because my error is growing like delta square root log m. I haven't chosen what delta is. I will choose some delta depending on what my target error is. But what I want is my eventual error to be small, to be vanishing. So I can tolerate m up to 2 to the little o 1 over delta square. That would be fine. If m is 2 to the little o 1 over delta square root log m will go to 0. I'll be fine, and I've created a number of clusters, which is 2 to the 1 over delta square. That's great. So that would be great. I would be done. Now, the question is, could m actually be much larger than 2 to the 1 over delta square? And the point is that it's not possible. Okay? M cannot be 2 to the little omega 1 over delta square. It cannot be 1 over delta to the 2.1. It cannot be that. This is where we'll use the Gaussian width. Remember, the Gaussian width of this process is bounded by 1. So this is like, just Sudakov minoration principle. It just says that if you have a set of vectors where the best delta, where you can create a delta packing of the set of size m. So means if you can find m different vectors which are all delta apart from each other, the expected soup is at least as large as delta square root log m. If you have many vectors which are all apart from each other, the expected soup is going to be large. Because you know that this expected soup is bounded by 1, you know m cannot be much more than 2 to the 1 over delta square. Otherwise, like the expected, the Gaussian width is, you will run into problem there, that the Gaussian width is constant, it's 1 for us. So it tells you that m cannot be 2 to the little omega 1 over delta square. Because otherwise the Sudakov minoration principle will say that the Gaussian width is not 1, it's omega 1. But the problem is that this leaves open the possibility that m is exactly 2 to the theta 1 over delta square, where you're not violating the width bounds on Gaussian width. And on the other hand, the error, which remember the error for us right now is delta square root log m, will become some constant. It's too large for us. We want a little o1 error. So this leaves open that possibility. And it turns out that indeed there are Gaussian processes where it doesn't matter what delta you choose. The best delta covering that you can do at every scale delta has size exactly 2 to the 1 over delta square. So it doesn't matter what covering radii you choose, it's not going to work. Any single radius clustering is not going to work. So we should choose a multi-error clustering. Multi-radii clustering. We should be more conscious of the geometry of the space we are dealing with. This is again like most of this thing. Thing is like well known that this is not one radii clustering is not good approximation. The clustering should be at math. And now we're going to use the heavy hammer here. We're going to use Talagrand's majorizing measures here. So what I'm going to do, I'm going to have it on the slide. I'm also going to write it. That clock is accurate, right? So I have like 20 minutes or something.
Yeah, that's just
yeah. It's not accurate. It's inaccurate in what direction?
+1.
Okay. Okay. I don't know which way the +1 is meant to. What is meant to?
Add an hour.
I want to. Okay, sure. 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 I'll keep talking when people stop leaving. It will be. Okay. Okay. So I'll write this and also write this here. But let's go over what the majorizing measure theorem says. It says if you have been given any set of vectors, admissible sequence is basically a sequence of partition of the vectors, where A0 is just do not partition. It's your entire set of vectors is just one cluster. And AN is a refinement of AN minus 1. Okay, so the most obvious thing you're doing. The number of partitions at the nth level you're creating is going to be at most 2 to the 2 to the n, doubly exponential in n. And now further, okay, so this is just a definition of an admissible sequence. And further, we're going to use the notation that if you chase any vector t, any vector indexed by t, A and t will denote the partition at the nth level of which t is a member. Okay, so if I choose any vector t, I'll say A and t is the set of is the partition at the nth level in which t lies. Okay,
the partition or the part?
The part, sorry, as a part. So creating a partition, sorry, I should say A and T is the part in which T lies at the nth level partition, sorry. And now what is the majorizing measure theorem? The majorizing measure theorem says that if you take any if you take any centered Gaussian process, there is a clever choice of an admissible sequence such that the expected soup is lower bounded by this quantity. Okay, the universal constant times go over every possible vector summation 2 to the n over 2 diameter of A and T. Okay, so let me write this down in a nice way. So the majorizing measure theorem is saying we start with the whole set of vectors like this, and then we are partitioning this, okay? Every vector, these are like, this is not a binary tree. At the nth level, the number of partitions going to be created is 2 to the n. But if you follow any particular vector, maybe here it lies first in the basic partition, then maybe here, then that vector would lie here as the parts go, okay? If you choose any particular vector and go down the tree of this partition we are creating, go down the tree, then summation 2 to the n over 2 times the diameter of the cluster in which it lies is always upper bounded by the expected soup. Okay. The majorizing measure theorem actually, it is always true that doesn't matter what admissible partition you create, admissible sequence you create, the soup of T over T 2 to the n over 2 diameter, this is always an upper bound on the expected soup. But there is a clever way to choose an admissible sequence that this is also a lower bound. So in some sense, the majorizing measure theorem completely characterizes the supremum in terms of these admissible sequences.
So what is, just to get a sense of why this factor 2 to the n over 2, somehow, how does it relate to like, for example, the n over 2, if you change it to 2 to the n, it would not be a good theorem.
And no, I don't think if you
n.
choose, no, it was 2 to the n over 2. It's really like if you have 2 to the n is the number of partitions you're creating, it's the square root of the log of the number of partitions.
So it's essential that this is.
Yeah, so I think it's not that 2 is not sacrosanct, but the point is that the number of partitions you're creating at the nth level, if you're putting a bound there, square root of the log of that number is the factor you're adding here.
So you're probably not going to need an algorithmic version if you want an algorithmic clustering of the vectors.
Yeah. So there's a way to do an algorithmic clustering. It's known. It's known that you can, given a set of vectors, this is the majorizing measure theorem can be constructive. Like you can make. Okay. So this is okay. So it's not obvious why this has anything to do with this thing, but at least it's creating some set clustering of vectors. It seems relevant because it's creating some clustering of vectors at every level. Okay, what is it at minimum saying? At minimum, it's saying that it's creating a clustering of vectors such that if you look at the nth level, the diameter of the nth level is smaller than 2 to the minus n over 2. I'm creating a set of clusters. Okay, choose any n. Let's choose n equals 100. Okay, then it's saying for n equals 100, I can take my set of vectors whose expected soup is 1. It can create 2 to the 100 clusters, and each of the clusters has diameter at most 2 to the minus 100 over 2. Why? Because otherwise, like the expected soup is 1. So you know that each term cannot be more than 1. But even more, each term cannot be 1 because the sum converges. So that is where, we cannot always have all the terms being constant. So that is where we hope to gain our leverage. Okay, I hope that gave some intuition as to why this is.
Anindya, so does this theorem itself imply that there are at most 2 to the n partitions, or is that?
This theorem says there's an admissible sequence,
right.
And the definition of admissible sequence is that at the nth level there are 2 to the n partitions. Yeah. So the definition of admissible sequence says that 2 to the n partitions is that this will happen. Hopefully that intuition made some sense. That we are creating, given an expected Gaussian process with one Gaussian with 1, any nth level, any n. this Talagrand's majorizing measure theorem will tell us that choose any n of your choice. You can partition your space into 2 to the n parts, such that the diameter of every part is at most 2 to the minus n over 2. But the fact that the sum converges means that it is saying a little more than x 2 to the minus n over 2. It's saying it's somewhat smaller than 2 to the minus n over 2. Yes.
Yeah, could you basically introduce how do you algorithmic construct this?
I do not know how they algorithmically construct this. The algorithm basically goes like, you look at the cluster, you look at your set of vectors and you say, what is this? You want to split it into two parts. Like suppose you want to split it into 4 partitions, you will say, I want to create my diameter as something. What is the Gaussian? What is the subset which has the maximum Gaussian width there, or maximum expected soup, and then iteratively construct? I do not have the entire construction like very clearly in my head, but this is not a very constructive process. Well, that is a randomized constructive process. You can also make it deterministic, but yes, sorry.
If you're doing it for small n anyway, you just try all partitions.
Yeah, for small n you can try out, well, I guess, yeah, for small n you can,
The constant n
Well, T,
well, the number of vectors T could be very large.
Oh.
Now, the deterministically, if you wanted to do it, the number of vectors could be very large.
so for every T, you will need to choose a different scale.
We'll choose a different scale. We'll have to, we cannot choose a single scale. And this is like, this is not an artifact of the proof. We know a single scale clustering will fail. Okay. So should we proceed? Okay. So this is what I was saying, like heuristically at the nth level, the diameter of the partitions should be a little smaller than 2 to the minus n over 2 because the sum is converging heuristically. And the number of partitions at the nth level is 2 to the n. So this delta square root log m, which was our error bound, should be smaller than 1. Heuristically, if this was true, like, the nth level partitions all have the same diameter, this would be immediately obvious. But of course, the nth level, the parts at the nth level need not all have the same diameter. So you have to work a little, but not much more. Okay, so now we are left with 2 questions. How to choose the clusters using the majorizing measure theorem? And if you partition the sets into clusters of different diameters, delta 1, delta 2, delta m, what is the total error we will incur? Earlier I said if it's the same error, same diameter delta, you have m clusters is delta square root log m. Now what is it? So let me address question 2 first. And then I will get to question 1. But really, it's from this point onward, it's really a matter of calculation. Not much needs to be done. So suppose you have clustered your points in different scales, delta 1, delta 2, delta m. What is the total error you would pay? And okay, what is the error we are talking about? Let's recall. So you have m clusters, B1 to Bm. They have diameters delta 1 to delta m. In each cluster, we are approximating the soup of the cluster by a single Gaussian plus a suitable constant. And again, if you recall, it's not just that the expected error between the soup of the Gaussian in that cluster vis-a-vis a representative is delta, but this Gaussian concentration property says that it's actually more than delta with probability at most 2e to the minus delta square over delta square, where delta is its diameter. So it's like a sharp concentration is there. Okay. This is useful for us. Why is it useful? So I've just again written that thing, that in each cluster, the error is more than any delta of our choice with probability at most 2e to the minus delta square over delta square. And simply applying a union bound, it says that for any delta of your choice, the total expected error would be delta plus the sum of all these error probabilities. Here, the union bound, I'm just using the fact that if you take any positive random variable, the expected value of x is at most, the expected value of x is exactly t greater than equal to 0 probability of x greater than equal to t, the integral of that. Okay, and that can be upper bounded by delta plus t greater than equal to delta probability of x greater than equal to t. This is just true for any random positive random variable. Its expectation is the sum integral over the CDF, which you can split like this. And now for that, so setting a particular value of delta and accounting for all the error after that using a union bound. It's just like, a couple of lines of arithmetic, really. Nothing more is going on. So this, I can choose any delta of my choice. So this is true for any delta that I want. Okay. Okay, so summarizing, what are we doing so far? We're saying my goal is to partition the space into m clusters, each with diameter delta 1 to delta m. I want m to remain small because that's the number of components in my sparsified process. And I want this choice so that this infimum over all delta, so there's a suitable choice of delta such that this sum remains bounded by epsilon. So I will eventually choose delta to be epsilon over 2. So my goal is to somehow get the remaining sum over s from 1 to m, this 2e exponential in this thing to be epsilon over 2. That's my goal. And what I have to do now is to choose the clusters using the majorizing measures theorem. And the way I'm going to do it is fairly obvious. You first set some n equal to n star. N star will be a reasonably large value we will choose. We will eventually choose. N star is like the base value we will choose, where we'll start looking at the majorizing measure theorem. It will be like log 1 over epsilon. And then what we do is we will, at the nth level, we will choose all the, sorry, should again say choose all the parts, not the partitions. Choose all the parts in your partition whose diameter is noticeably smaller than 2 to the minus n over 2. 2 to the minus n over 2 is like the bound we do not want to choose. So I'm just choosing a little smaller than that. Delta times 2 to the minus n over 2. That's what I'm going to do. Whichever points already got in my partitions, great. Otherwise, I go down the tree and I.
Yeah, this delta is already chosen to be epsilon over 2.
Delta is already chosen to be epsilon over 2. And as long as there is some t which remains uncovered, I continue the process like this. Okay. The first point is that the process will stop rather quickly within 1 over delta steps. Why? Because note, every time I do not choose a particular point, this 2 to the n over 2 times diameter of n a n over t is contributing delta. I know that every part on my thing has to terminate within one sum. So this process cannot go on for more than 1 over delta. So this is a completely finite process. That's great. If you now plug in the numbers and you look at the error induced by our clusters, well, when the part P is selected at the nth level, the diameter, I know we chose it because it's delta times 2 to the minus n over 2. So the contribution you get from there is exponential. If you just plug in the number, you get if a part gets selected at the nth iteration, it's at most exponential minus 2 to the n plus 1. That's just plugging the numbers here, really, because delta squared divided by delta squared times 2 to the n over 2 to the minus n. That's what I'm getting. So this sum, since the number of partitions at the nth level is bounded by 2 to the n, if I only select partitions for n sufficiently large, this is just arithmetic, there's nothing to see here really. You just plug in everything and the first term dominates everything else. So the total error is delta plus 2 times e to the minus 2 to the n star. So we'll set delta equal to epsilon over 2 and we'll set n star equal to log 1 over epsilon. The total error would be epsilon. This is just the error analysis. How many partitions do we create? Well, process terminates by n equals n star plus 1 over delta, which is dominated by order 1 over delta, so order 1 over epsilon. The total number of partitions we have created is at most 2 to the 1 epsilon. So, okay, so this is the last few slides, so just arithmetic really. But all we did is we used the majorizing measures theorem and said, I can just go back there. all we did is we started at a sufficient point in the majorizing and the tree created by the majorizing measure sim, and we just do this thing and say, choose any part whose diameter is sufficiently small vis-a-vis the 2 to the minus n over 2 thing. Choose all those parts. If something doesn't get covered, continue. That's all. And just the guarantee of the majorizing measure theorem will immediately tell us that this process cannot on forever in order 1 over delta steps. This has to stop. And the error bound, when you do the error bound, it will show that the total error you create is actually small. And this error bound that we're creating for m different clusters is nothing more than a union bound, really a cleverly written union bound.
So this is somehow like also characterizing your theorem, right? Saying that if you have the small width, then you're essentially supposed to be clustered. Maybe the clusters are not the same diameter, but you're essentially supposed to be clustered.
Yeah, exactly. Yeah, so if the diameter is smaller, essentially, suppose it is because you have finite number of you will be able to find a small number of parts in which the space excludes. Yes.
To help me understand the proof, if the original vectors are all just like independent coordinate vectors, then what is your construction? Like if you unravel all of this.
Well, the Gaussian width won't be 1 if you have more than constant number of vectors.
Normalized.
Then what would happen to the majorizing? What would be the tree given by the majorizing measure theorem? Well, actually, sorry. So I know how you can approximate it by a small dimensional thing immediately. Actually, that one is really simple. So to normalize, what you would do is you will normalize the vectors by 1 over square root log n. If you have n independent vectors, unit vectors, E1 to En, you divide by square root log n, square root log n, square root log n, this expected soup is 1.
Sure.
What the construction will do is it will just put all of it in one blob, just one ball. And just say the soup, the random variable, which is the soup of these n independent vectors, is just very closely approximated just by a constant. Because the variance is very small.
The variance is 1 over square root log n.
Yeah, which is like asymptotically vanishing.
Okay, I think that helps.
So it will not approximate the process in any way because two or normal systems will be approximated by the same constant.
Two orthonormal system will be well, it will not approximate it will be approximated by the same constant. So it is not approximating beyond this.
Yeah, so in particular what I said in the beginning, you cannot hope to get there.
This is just true in general. Like if things are constant, like if the max is concentrated, then you will just output a single vector.
Yeah, if the thing max is concentrated, you will just output a single vector. Yeah. I guess I'm out of time, so let me just recap everything that we did. That we start with the Gaussian process. We assume we normalize things so that this Gaussian width is 1. And then we consider this admissible sequence. So that's the major hammer given by majorizing measures theorem, which says that there's a way to partition the space so that if you look at any particular point, the parts in which it lies, the diameters are smaller than 2 to the minus n over 2 at the nth level, but not just that, it's significantly smaller in the sense that the sum will always converge to order 1. And one can basically use this admissible sequence to partition the space, but the number of partitions is exponential. That's epsilon. And once you do this, you choose a representative vector for each of these partitions and a suitable constant, the constant just being the expectation of the residuals you have there. And that is a good enough approximation for Gaussian. A super Gaussian. That's all. Thank you.
Questions? I have one. Does it work? For it seems extremely sensitive to the choice of Gaussian. any other distribution, suppose you have even your sub-Gaussian, something that is even falling faster.
Or Rademacher's. Just
Rademacher's, there was a potentially it could work. Sub-Gaussian, I would say, really the hard part of everything that really everything that's being used is this statement really I mean things will fall apart because, for example, this may not be true if you had sub-Gaussian random variables. This kind of anti-concentration, this kind of if you have so many vectors, it will be this. So Rademacher's is a particularly interesting case because there's this famous result now that if you have a Bernoulli process, which I suppose is nothing but soup of W inner product with independent plus minus one random variables, if that is a constant, then we know that the set of vectors is always a subset of two sets. So I can maybe write here rather than it's easier to write. Okay, so if expected soup of Vx is, let's say, order 1, where x's are being drawn from plus minus 1 to the n and not Gaussian, and soup of V in T, then this set T is a subset of T1 plus T2, where we're thinking of this plus in the Minkowski sum sense, where T1 is a set of vectors with small L1 norm. So that's one way a Bernoulli process will bounded soup. And T2 is corresponds to the Gaussian setting.
This is same as sum of sparse vector and whatever comes out of the the Gaussian thing. Are the only other examples that need to consider sparse vectors?
Yeah. So basically, you could you could have only other genuine examples as sparse vectors, or whatever is a Gaussian thing, and it's like a Minkowski sum of both. It would be fine. I don't know how to. I mean, the proof of this is apparently very, very difficult. I do not know the proof at all. I don't know. It's very difficult for me. I don't know how this proven. I think Latala and Shivam, do you know who proved this?
Bednorms? Yeah, Bednorms.
Okay. So this was open for the longest time. I think Talagrand. This was one of Talagrand's well-known open problems. One could ask that maybe this is if one tries to use this, maybe one could show that if any time the expected soup of a Bernoulli process is small, is it because it could be, is it well approximated by? I don't know how to finish that sentence really. It's well approximated by something which has a small L1 norm plus a low dimensional thing. Maybe that's true, maybe that's not true. I would just like to point out, Pravesh can tell you this because it's his theorem. What is that there's a little more analogy, because if one thinks about convexity as the continuous analog of submodularity, then every submodular function can be approximated by a low dimensional function, by a junta. That's true. I'm trying to think if that is there is some correspondence there, that if one can show that every I don't know, the soup of these random variables, soup of these linear functions is submodular functions. Is it submodular function? I do not know.
What was your original motivation for studying this?
Oh, the original motivation for studying this was the application I did not mention. We were thinking about asking this question, whether every constant with polytope can be approximated by a polytope in few dimensions over the Gaussian space. Because the analog of this statement over the Boolean hypercube is true. Every constant with CNF or every constant with CNF or DNF could be approximated by CNF or DNF with only the number of variables which is only dependent on the width under the uniform distribution. So you're asking, okay, if there's a continuous analog of this statement, CNF mapping to polytopes, uniform distribution of the cube mapping to Gaussian distribution.
Gaussian case doesn't follow via CLT.
CLT over what?
Like for instance, you can deduce stuff like Gaussian X-over from the one for Bernoulli, say.
Yeah, but usually, okay, I mean, it depends on what you're going to use, but I think mostly CLTs would have some deterioration, among other things, based on how many, if you're trying to apply high dimensional CLT, almost certainly a number of constraints you're going to put, how many half spaces, how many number of polytope, how many facets the polytope has will play a role. But here the whole game is that we don't want to pay anything in terms of the how many facets the polytope has. The ideal theorem, which we know is true now, we'd like to prove, is that if you take any polytope over R to the n, and suppose it has constant width, so all the separating hyperplanes are at constant distance from the origin, then there is another polytope which is only defined using a constant number of facets, okay, and the other dimensions would be left free, such that this new approximator polytope and the original polytope would have small Gaussian, the symmetric difference would have small Gaussian.
I mean, what I'm suggesting is like you take this polytope in Rn, you embed it into like dimension like n times k, let's say.
Okay.
Like now, where you can relate the. these
But the sparsification that is known in the Boolean world is for CNFs and DNFs, not for arbitrary half spaces.
Okay.
Does that make sense? Like CNFs and DNFs can be seen as intersection of half spaces, where all the weights are like 1, 1, 1, 1, and the threshold is put at like n-1 or something. But we are not trying to do so. You could try to do that, but it won't map to the things we already know to be true.
So yeah, I want to go back to Avi's question and just ask one thing about Rademacher's. So if all the vectors that you had were, let's say, plus minus 1 coordinates, so perfectly flat.
Okay.
And I was taking this Rademacher process.
Okay.
Then does your theorem immediately yield the same result? Like the intuition being that, for flat vectors, Rademacher should be basically Gaussians.
Flat vectors, and you want them to be dense or something? Because
yeah, flat I mean like the coordinate is no larger than like the
1 over something. Okay. I don't know because again, ideally would like to say why is the Gaussian process, why is Gaussian equivalent to Rademacher, like in this kind of sense, like the Rademacher, what Rademacher would do would be because of central limit theorem kind of things. Right? Like one vector, one Gaussian thing, and one Rademacher thing would be same up to some error, maybe 1 over root n error, let's say. If you have collection of the Gaussian collection would be equivalent to the Rademacher collection, but you will pay, the error you would pay would depend on how many you have, how many of these vectors you have. The whole thing is you don't want to pay anything here. So I don't think you would like, I don't know, my feeling is that it might not be it might be true, but it might not be a black box application of what's.
I think Pravesh was saying in that situation, you could take T1 to be empty so that the Rademacher process would be lower bounded by the same majorizing measures.
As in like you do have anti-concentration, so I mean at least the requirement you wanted is met now, right? Like the hypercube is not concentrated only in sparse directions. So I've removed that barrier.
Okay.
So, yeah, but I think Sinho has like a more concrete version, I says.
They're saying that I have, I don't know, I mean, I see like, that my initial objection that you won't have this kind of delta square root log m kind of thing is removed, that objection is removed. I do not know the rest of the thing, how it will go through.
I guess you need this theorem to apply to whatever T2 is.
Yeah, but that would probably just rule out like m equal to, like, this thing, like initially we were playing this thing, right? Oh, m cannot be too large or too small. Probably that objection is removed, but to eventually get some convergence here, we need the majorizing measure theorem. I do not know if, like suppose you had like a Bernoulli process where you are told all the vectors are plus minus one, none of the vectors are, all the vectors are very dense, they are all flat. Does the majorizing measure theorem hold? I do not know. I don't know. I absolutely have no idea whether it holds or not.
You mentioned there was a construction of vectors for which you can get sparsely better than x of 1 over epsilon. That is describer.
We cannot get better than 1 over epsilon. Yeah.
Yeah, can you describe what the construction?
Good. The construction is, I'll try, but probably make a mistake, but Shivam can correct me. Where's the I think the following should be true, like, just take the set of vectors, which is so should we remember what the construction is? I'm sorry. It's like how much do you weigh? Like it's like a shifted, like each vector. Okay, let V be the let S be the set of unit vectors in R to the n. Okay, for each V in S. I will put a vector, I'll create V prime, which is equal to, I want to say 1 minus 1 over root n times E naught. So I'm adding a new dimension. This is like in n dimensions, I'm adding a new dimension, E naught, okay? Plus 1 over root n times V. So this, I'm creating a new set of unit vectors, almost, yeah, unit vectors. This is my set of vectors, okay? So I've created infinitely many. It doesn't really matter infinitely, you can sparsify it and create only to the omega and many vectors. So this basically take every vector corresponding to the ball, make it smaller by 1 over root n, plus add like a constant, plus add like one big unit vector in that dimension. So the expected soup of this, now if you look at expected soup of this Gaussian process, V prime in, if I call the corresponding set you create as S prime, V prime dot X, it would be order 1. Because these vectors 1 over root n will only contribute 1 n. And this. But what you can show is that if you wanted to approximate this Gaussian process with this Gaussian with this 1 to error epsilon, which is smaller than 1 over root n, okay, you would require at least 2 to the root n vectors. So this would give because n is free for us to choose, this would give a 2 to the 1 over epsilon lower bound. Okay, the fact that for any such process, you would require 2 to approximating this thing with error 1 over root n or smaller requires 2 to the root n lower bound, at least 2 to the root n such vectors is something that is there in another paper with Rocco and Shivam. So, but yeah, this is the thing. It's like basically take the unit vectors, scale them down so as to make it a unit with process. Take all the set of all unit vectors. That's
More questions? All right, thanks.
okay. Thank you.